Welcome back, everybody. We're diving into something pretty fascinating this time. A brief history of intelligence, evolution, AI, and the 5 breakthroughs that made our brains.
Oh, this is a good one.
Yeah, I was really excited to dig into this. This book by Bennett. It's kind of like a detective story.
Yeah.
You know?
Yeah.
Piecing together all these clues
Mm-hmm.
from neuroscience and AI and evolution,
Yeah.
all to figure out how our brains got to be so good at, well, everything. From just like walking around to
Right.
writing symphonies.
It is pretty wild when you think about it that way.
It is. It is.
Like the range.
Yeah.
Yeah. And the book really takes you on this journey through the history of life on Earth, basically. It starts with single-celled organisms and goes all the way to us, humans. And Bennett, he uses this idea of like breakthroughs.
I like.
Yeah, these key moments in evolution that really pushed intelligence forward.
Yeah, I love how he brings together like insights from so many different areas. Like he'll be talking about dopamine in the brain.
Right.
And then suddenly he'll bring up Minsky's Senark, that old AI experiment.
Yeah.
And it's amazing how those early attempts to make like thinking machines
Yeah.
can help us understand how our own brains actually work.
Totally. It gives you a new perspective on things. And he throws in these fun little historical stories, too. Like, remember that part about the researcher who, kind of by accident, discovered place cells in the hippocampus while he was studying how rats navigate mazes?
Oh, yeah. It makes the science come alive.
Totally. It feels like you're right there with those researchers figuring things out.
Yeah. Okay, so let's get into the book. Like, right away, Bennett focuses on how important energy is. Like, it's the fuel for life, right?
It's at everything.
And how organisms get that energy that really shapes their whole evolutionary path. He takes us way back to the very beginning.
Yeah.
Those early life forms using hydrogen.
Mm-hmm.
And then, bam, photosynthesis. That was a game changer.
Huge.
Absolutely. And he makes this really interesting point about why animals, unlike fungi, went on to evolve neurons and eventually complex brains.
Yeah, I was wondering about that.
And it all comes down to movement.
Okay.
Like fungi, they just sit there and absorb nutrients from their surroundings, right?
Right. They don't have to go anywhere.
Exactly. But animals, we got to hunt. We got to avoid getting eaten.
Yeah. So we need a way to sense what's going on and react, right?
Exactly. So that need to move,
Yeah.
that's what drove the development of the whole nervous system.
It's the foundation.
It's the foundation.
Yeah.
And then on top of that, all these other breakthroughs happened.
Right.
Bennett calls that first big one steering,
Okay.
which is basically just the ability to navigate, to move around.
Right. Makes sense.
Think about simple organisms like nematodes.
Okay.
They don't have maps, they don't have GPS,
No.
but they can sense changes in their environment.
Yeah.
And they react, like basic sensory input,
Okay.
chemical gradients,
Okay.
and something called valence neurons.
Oh, tell me about those. I don't think I remember that part.
Oh, they're so cool. Valence neurons, they basically decide if something is good or bad.
Interesting.
So it's approach or avoid.
Okay, so like if the nematode runs into a delicious smell,
Uh-huh.
the valence neurons go, good, and it moves towards it.
Exactly. But if it encounters something nasty,
Yeah.
different valence neurons fire, signaling bad. Get out of there.
And it wriggles away. That's pretty clever for such a simple organism.
Right. It's like a built-in system for knowing what's good for them and what's dangerous,
Yeah.
helping them navigate this complicated world.
Makes sense. And it kind of ties in with this idea of affective states. I remember that part, like those persistent feelings that influence their decisions.
Oh, yeah. Like imagine the nematode catches a whiff of food.
Right.
Even if the smell goes away, that feeling, that affective state, sticks around. It keeps the nematode searching in that area.
Yeah. So it's not just a fleeting reaction. It's like a little bit of, motivation?
It is. It's basic motivation. Like, seek out what's good, avoid what's bad.
Yeah, that makes sense.
And it shapes their behavior in this really fundamental way.
It's like the foundation.
It is.
And this leads to another cool concept, associative learning.
Yeah.
Even these simple guys, like nematodes, they can learn to associate certain things with good stuff or bad stuff.
Right.
And that ability to link cause and effect, that's huge. It's basic survival stuff.
Totally. So learning, it's not just about complicated thought processes. It's built into those simple nervous systems, too.
Exactly. And Bennett points out how tricky this is computationally. Even this basic ability, like one problem is what he calls the credit assignment problem.
Oh, yeah. Like, how does this tiny little brain figure out which cue
out of all the noise.
Exactly. Is responsible for something that happened, especially when there's a delay between the action and the consequence.
Yeah. It's like trying to figure out what caused what when so much is going on.
Totally. It seems like a real brain twister for these little guys.
Yeah. It is. But evolution has some tricks up its sleeve. Like maybe the brain focuses on the strongest cue or the most recent one, or it ignores cues that are always there,
Right.
or it blocks out stuff it's already learned.
Right. So they're not just passively responding, they're actively filtering and prioritizing information.
Exactly. It's pretty impressive when you think about it.
Yeah. So these seemingly simple mechanisms are actually pretty sophisticated.
Oh, yeah.
And they're setting the stage for those more complex forms of learning that we see in, higher organisms.
Absolutely. And that takes us to the second big breakthrough, reinforcement learning.
Okay.
This is where things get really interesting.
Yeah.
This is where we start to see more complex behavior driven by rewards and punishments.
Okay, so it's not just reacting to what's right in front of you. It's about learning from what happens because of your actions.
Exactly, and changing your behavior because of that.
I see, I see.
Think of Thorndike's puzzle boxes.
Oh, right. With the cats.
Yeah. The cats had to figure out how to escape to get their treat, and they'd try all these different things, and the stuff that led to the reward got stronger, and the other stuff, well, they didn't do that as much anymore.
So it's like a refining process. Your actions get shaped by the feedback you get.
You got it. And this is where the link to AI research gets really cool. Like those early attempts to replicate this kind of learning in machines. Like, remember Minsky's SNARK?
Yeah.
They hit some snags.
Really?
Oh, yeah. They had trouble with what's called the temporal credit assignment problem, like figuring out which action in the whole sequence of actions actually led to the good stuff or the bad stuff.
Yeah. I can see how that'd be tough.
It is. It's like untangling a big knot of cause and effect.
Totally. How did they solve that?
Well, they realized that just giving rewards or punishments for single actions wasn't enough.
Okay.
The trick was to look ahead, to focus on predicting future rewards.
I see. Like planning.
Kinda. Bennett calls this temporal difference learning. And it's a big deal both in AI and how our brains work.
So it's not just about the immediate reward. It's about learning to anticipate what's coming next.
Exactly. Like becoming a chess master, seeing moves ahead.
Right.
And this is where dopamine comes in.
Oh, dopamine. It's not just about pleasure, right?
No, it's about the anticipation. Remember those monkey experiments where they learned to link a light with a reward? Their dopamine neurons fired, not when they got the treat, but when they saw the light, the predictor of the reward.
That's so cool. So it's that feeling of, maybe I'll win this time.
Yeah, and this whole dopamine system is wired to a part of the brain called the basal ganglia, which is like this amazing learning machine. It's always comparing its predictions to what actually happens, updating its models, refining its actions based on feedback, all driven by dopamine.
So we've gone from simple steering to this complex system of learning by rewards, driven by dopamine and this incredible learning machine in our brains.
You got it. And that ability to learn and adapt, that sets the stage for something else that's fascinating. Curiosity.
Oh, interesting.
It's not just about chasing the next reward. It's about exploring, trying new things, pushing the boundaries.
So it's that classic explore-exploit dilemma.
Exactly. Do you stick with what you know or venture out?
Right.
And that exploration, trying to understand the world, that's tied to another key player. The cortex.
Yeah.
It's like a massive pattern recognition machine evolving to help us make sense of all the information out there.
So it's not just reacting, it's building a model of the world.
Yeah.
Recognizing patterns, using that to make better decisions.
Exactly. And that leads us to the third big breakthrough that Bennett dives into, pattern recognition.
Pattern recognition.
It's way more complicated than you think. Like even programming a computer to recognize an object, no matter how it's turned or lit, that's super hard. Animals had to solve similar problems.
Yeah. It seems so simple, but when you really break it down, it's incredibly complex.
It is. And here's where we get into those ideas of discrimination, being able to tell similar things apart, and generalization, knowing that similar things belong together.
Right.
And Bennett takes us into the structure of the cortex here, highlighting this theory by Mountcastle about the neocortical column.
Okay.
It's basically a tiny repeating circuit, like a miniature learning machine copied over and over.
Wow.
So the brain can learn new things super flexibly.
So it's like a modular system, each little column doing its own thing, but together they make this powerful network for understanding the world.
That's a great way to put it. It's more adaptable than our best computers.
Yeah, yeah. But even with all this, there was still a big challenge. Catastrophic forgetting.
Oh, right. That's a big one.
Like, imagine teaching a neural network to recognize cats,
Mm-hmm.
and then you teach it to recognize dogs, and it forgets all about cats.
Yeah, that's not ideal.
Not ideal.
Hmm.
How did our brains overcome this?
Well, that's still a bit of a mystery. We don't totally know how our brains pull off continual learning, constantly updating our knowledge without forgetting the old stuff.
Yeah.
But Bennett points to some cool possibilities, like how these things called convolutional neural networks, CNNs, in AI,
Okay.
they solve the invariance problem, being able to recognize stuff no matter where it is or how it's rotated.
Oh, interesting. So it's like our brains have some secret tricks we haven't figured out yet.
Totally. And the story of pattern recognition doesn't stop there. We're about to enter the world of primates,
Oh, yeah.
where things get even more complex. Social pressures,
Yeah.
understanding other minds, those drove some big evolutionary changes.
That's where it gets really fascinating. The rise of the social brain, theory of mind, and eventually language. These breakthroughs set primates, and eventually humans, apart from everyone else. But we'll save that for the next part of our deep dive.
Thank you for listening to Rambling Dan Rowe's Deep Dive Book Reviews. Please help support our channel by clicking the like and subscribe button. Thank you.
All right, so let's get back to where we left off. Primates. And this incredible thing Bennett calls the fourth breakthrough, mentalizing. This is where we really start to see the seeds of what makes us human. But before we get there, we need to rewind the clock a bit. Way back to that crazy event that kind of reshaped life on Earth, that asteroid that wiped out the dinosaurs.
It's mind-blowing, right? Like hitting the reset button on evolution. It's what allowed mammals to thrive and ultimately led to us.
Exactly. And for our early primate ancestors, this event, it was a game changer. They found refuge in the trees, and it shaped their bodies and their brains in these profound ways. They got those opposable thumbs for gripping branches, their vision got super sharp navigating a 3D world, and their diet changed too. More fruit, which made foraging a lot more complex.
It's like this whole arboreal lifestyle, living in the trees. It really set the stage for so many adaptations, not just physically, but mentally too.
Absolutely. Primate life is inherently social. Living in groups, it brought new challenges and opportunities. They had to figure out these complex social hierarchies, form alliances, compete for resources and mates. Bennett describes how primates spend a huge chunk of their day just socializing, grooming, playing, all these intricate interactions. He calls it an arms race for political savvy.
Like, you got to be able to read the room.
Exactly. Being able to figure out what others are thinking, that becomes crucial for survival.
It's fascinating to think that that kind of social pressure, that need to outmaneuver your rivals and find your place in the group, might have driven the evolution of the parts of the brain involved in social intelligence.
That's precisely what Bennett argues. He talks about this pivotal study where they showed how strongly primates react to any violation of social hierarchy. Like, if a lower-ranking individual tries to boss around a higher-ranking one, it causes total chaos. It's like they have this built-in sense of social order, and messing with it, it just doesn't fly.
So it's not just about recognizing who's who. It's about understanding where they fit in the pecking order.
Right. And then anticipating how they'll behave based on that.
That's amazing.
And this sensitivity to social dynamics, well, it likely fueled the evolution of those brain regions involved in mentalizing. The ability to get that other individuals have their own thoughts, beliefs, desires, and intentions.
It's like developing this model of the mind, not just your own, but of others too.
That's a perfect way to put it. They're not just reacting to behavior anymore. They're trying to understand the why behind the what.
I see.
And Bennett points to this area of the brain called the granular prefrontal cortex, the GPFC. It got a lot bigger in primates, and it's like this extra layer of processing that allows them to simulate mental states and predict actions.
So this ability to mentalize, it had some pretty big implications, right? It's like the foundation for so much of what makes us human. Empathy, cooperation, even deception and manipulation.
Absolutely. Bennett argues that mentalizing was absolutely key for something we call imitation learning. Think about how we learn. We watch others, we try to figure out their goals, we refine our own techniques based on what works and what doesn't.
Right.
It's insanely powerful. It's how knowledge and skills get passed down.
It's like the basis of culture itself.
Exactly. And Bennett points out that imitation learning, fueled by mentalizing, might have even given rise to active teaching. Instead of just watching, adults could actually demonstrate skills in a way that made learning easier, breaking complex actions into smaller chunks and giving feedback.
Interesting. So they became more deliberate about sharing knowledge.
Right. They understood that the learner needed specific information to succeed.
It's a whole other level of teaching.
And this shift towards active teaching, made possible by theory of mind, it had a huge impact on primate intelligence. It really sped up the transfer of knowledge.
I see. So we've come a long way from early primates navigating the complex social life of their groups to understanding other minds, which then leads to teaching, learning, culture. It's like each step builds on the last one.
It really is remarkable.
Yeah.
And that momentum, it keeps going. Bennett says mentalizing didn't stop there. It also played a crucial role in our ability to think about the future, what he calls anticipatory cognition.
This is where we start seeing those truly human qualities. Planning for the future, delaying gratification, making decisions that benefit us later on, even if it means sacrificing something right now.
Exactly. Remember those persistent affective states we were talking about? The ones that guided those simple organisms?
Yeah.
Well, primates took this idea and ran with it. They developed the ability to act on a need they weren't even experiencing at the time.
Okay.
It's thinking ahead. Gathering food when you're not hungry, building shelter before the storm hits, saving resources for tough times.
That's incredible.
It is. It's like breaking free from just reacting to what's happening in the moment. And this ability to plan for the future, it probably relied on those same mentalizing brain regions. It's running simulations, picturing yourself in the future, realizing your future self will have different needs.
It's almost like time travel, but in your mind.
That's a great way to put it. And this ability to think ahead, combined with theory of mind and imitation learning, it set the stage for something truly extraordinary: language.
Language.
Yeah.
That's the final breakthrough in Bennett's framework. And arguably the most transformative. This is where we go from primate intelligence to human intelligence.
Yeah.
Being able to share complex ideas, knowledge over huge differences, building on the wisdom of countless generations. It's like unlocking this whole new level of possibility.
You said it. And while language is a whole complex topic, with roots going way back in our lineage, it's with humans that it just explodes in complexity and power.
Right.
It's like a totally new operating system for the brain.
It really is. We've come so far from those single-celled organisms just sensing their surroundings to humans pondering the vastness of the universe, writing poetry, making music, building entire civilizations, all because of the incredible evolution of our brains.
It's an amazing journey, but there's still so much more to unpack when it comes to language. How it works in our brains, its role in human culture, and even its connection to artificial intelligence.
So we've made this incredible journey through billions of years of evolution, from those first simple organisms to the emergence of primates and their incredible social brains. Now it's time to dive into the final chapter, language, the fifth breakthrough in Bennett's framework.
Yeah, this is where all comes together, all those previous breakthroughs: steering, reinforcement learning, pattern recognition, mentalizing. Language takes all of that and amplifies it, creates a whole new level of cognitive potential, like unlocking a new dimension of thought and communication.
Bennett really emphasizes how unique human language is. It's not just signals for danger or attracting a mate like we see in other animals. It's sharing these complex thoughts, abstract ideas, even stories about the past and the future. So how did this evolve? What happened that made us the talking ape?
Well, Bennett takes us back to those early hominids who left the trees and started living on the African savanna. This change, this move to a terrestrial lifestyle, presented new challenges and opportunities. They had to adapt, not just physically, but cognitively too. They had to coordinate hunts, protect themselves from predators, and navigate a much more complex social world.
So it wasn't just about walking upright. It was about adapting to a whole new way of life that demanded more cooperation and communication.
Exactly. Imagine those early hominids scavenging for food, hunting together, defending themselves. They needed to communicate about threats, share information about resources, develop strategies to work together. This growing need for social cooperation probably played a big role in the evolution of language.
It makes sense that a more complex social environment would require a more sophisticated way to communicate. But Bennett also talks about the role of tools and technology.
Oh yeah, that's a good point. As our ancestors developed more sophisticated tools, they needed a way to share knowledge about how to make and use them. Take crafting a hand axe or building a shelter. Those skills weren't easy to learn just by watching. Language provided a way to transmit that knowledge, to explain the steps involved, to troubleshoot
So
problems.
language wasn't just about describing the world, it was about shaping it, passing on this knowledge that allowed us to modify our surroundings and increase our chances of survival.
You got it. And as language evolved, so did our capacity for abstract thought and planning. We could talk about hypothetical situations, imagine possibilities, create these shared narratives that brought us together. This ability to go beyond the here and now, to share mental models of the world, that's what sets us apart.
Language became the operating system for human culture, letting us build on the ideas of those who came before us and create increasingly complex societies. But let's shift gears a bit and talk about the brain. What's happening in our brains that actually makes language possible?
Bennett gives us this really fascinating tour of the brain, pointing out these key areas involved in language processing, like Broca's area, which is essential for speech production, and Wernicke's area, which is involved in understanding language. These areas are primarily in the left hemisphere of the brain, and they show that language isn't just a general cognitive ability. It has its own specific neural circuits.
So it's not just about having bigger brains than other primates. It's about specialized areas in our brains that are dedicated to language.
Exactly. And while we're still figuring out all the details of how language works in the brain, Bennett does highlight some important insights like joint attention. That's the ability to share focus on something with another person. It turns out that's really important for language development because it allows babies to learn the names of things and understand the intentions behind communication.
Like when a baby points at something and looks back at you, as if to say, hey, look at that. It's not just observing, it's actively sharing an experience.
Yeah.
And that lays the groundwork for language.
You got it. And that ability, along with our long childhood and constant interaction with caregivers, it creates this perfect environment for learning language. We're surrounded by language from the moment we're born, and our brains are built to soak it all up, decode those sounds, make sense of that complex system of symbols.
Our brains are practically pre-programmed for language,
Mm.
but that programming needs the right environment to be activated.
Exactly. And that leads us to a question Bennett tackles head on. If language is so ingrained in our biology, what does that mean for artificial intelligence? Can we recreate that ability in machines?
It's the big question everyone's asking these days.
Mm.
We have these large language models, LLMs, like GPT-3 and GPT-4, that can write all sorts of creative content and answer your questions in an informative way. So does this mean we're close to having machines that truly understand language?
Well, that's where it gets really interesting. These LLMs are pretty impressive, but they're still missing something fundamental. They don't have common sense and they don't truly understand. They can put words together grammatically, but they often struggle with the meaning, the context, all those nuances that humans understand without even thinking.
So they're good at the structure of language, but not the meaning.
Exactly. Bennett gives some great examples, like asking an early LLM what you'd see if you looked up in a basement. It might say the sky, completely missing the point that you're in a basement.
Right. They're missing that connection to the real world, that understanding of how things actually work. Amazing at pattern recognition, but not quite there yet when it comes to the kind of intelligence humans have.
Precisely. And that highlights a big difference between human intelligence and artificial intelligence. We've evolved over millions of years to navigate a complex, messy, unpredictable world. Our brains are shaped by experiences, by interaction, by this constant back and forth between what we do and how the world responds. AI systems are still pretty isolated from all that.
So it's more than just processing power or the size of their data sets. It's about how our brains are wired, how we learn, how we make sense of the world through our senses and actions.
You got it. And while AI research is advancing at an incredible pace, Bennett argues that we're still a long way from truly replicating human intelligence, especially when it comes to things like language, understanding, and common sense. But who knows what the future holds?
It's both exciting and a bit unnerving to think about the possibilities. A Brief History of Intelligence has been a wild ride, exploring what our brains can do and what that means for us.
It really makes you think about what it means to be intelligent, appreciate the long history that brought us to where we are, and consider those possibilities and challenges of artificial intelligence as it keeps evolving.
Absolutely. If you enjoyed this deep dive into intelligence and those 5 incredible breakthroughs that shaped our brains, we highly recommend you check out A Brief History of Intelligence by Max Bennett. It'll give you a whole new appreciation for the amazing power of the human mind. Thanks for joining us.